just a little bit more that of taking integrals, it ends up dealing with a log rule. All right, and here's just a quick review of what we did last time. It says, hey, as long as we notice the pattern that we have the derivative of the bottom up on top. So here's the derivative of the bottom. As long as we have that up on top, we can take a very easy integral and just say, okay, well, it's the natural log of the stuff. Remember how he's always said it's when we were taking the derivatives of natural log, it was the derivative of the stuff over the stuff. Well, this was what I was calling the stuff. Notice, if we can notice the pattern saying, okay, the derivative of the bottom, so the derivative of the stuff is on top, we can take a very easy integral, so it's just going to be the natural log of the bottom. So knowing that, all right, we can go ahead and still evaluate area underneath the curve as well. So it says find the area of the curve of the region bounded by the graph. So y equal to x all over x squared plus 1. The x-axis and the line x equal to 3. So it gave us our upper and lower bound. It said from 0 to 3, right? Okay. So we're going to take the integral of x all over x squared plus 1. Well, when we take the derivative of the bottom, we notice that the derivative of the bottom is 2x, not just x. So we actually have to do something in order to get the top where we want it. So actually we need to multiply. We need to have a 2 up top. Well, if we do that, we can't change the equation. Right now I changed the equation. All right. If you agree, if I can multiply this whole thing by 1, we don't really change the equation. So if I multiply by a 2 on the top, I better divide by a 2. So what we end up doing is we pull a 1/2 to the outside. So it's like multiplying the entire equation by 1. I just have now the derivative of the bottom up top. So now I can say the integral of 2x all over x squared plus 1 is, well, 1/2 is still on the outside, the natural log of x squared plus 1. And that is going to be evaluated then at 3 and 0. So I have 1/2 times, let's see, let's evaluate 3. I have 9 plus 1, so the natural log of 10 minus, let's see, when I plug 0 in there, so you go top minus the bottom, I'm going to get the natural log of 1. Well, we know from our natural log rules that the natural log of 1 is just 0, so that ends up going away. So we can say 1/2 natural log of 10. And we can figure out what approximately this equals by using our calculator over here. We have a natural log button right here. So we need to go, let's see, 1/2 times the natural log of 10. And we get 1.15 and so forth. All right. So we can type that in our calculator, figure out what the actual area is underneath that curve from 0 to 3. Moving on. Again, now you'll notice we have more examples. Look at the pattern. The first thing you do is check, does the derivative of the bottom equal the top? Well, yeah, I'm going to take the derivative of x cubed plus x, and I'm going to get 3x squared plus 1. Well, we have a very easy integral then, don't we? So it's just going to be the natural log of the bottom, x cubed plus x. All right, same thing with 2. The derivative of tangent, secant squared. Very easy, the natural log of the bottom. Same thing here, except for we're going to be a little off. All right, if I take the derivative down here, I'm going to get 2x plus 2. Well, you notice all I have to do is multiply this top by 2, and I'm going to have my derivative of the bottom up top. Well, I can't really multiply. I can't change the equation. If I put a 2 up top, I also have to put a 2 on the bottom, so I'm going to have a 1/2 on the outside. So this is going to equal then the 1/2 natural log of the bottom, x squared plus 2x. All right. And obviously, sorry about that, I forgot my plus c's. So every single one of these should have been plus c's. Plus c, plus c, and plus c. All right. Moving on. Oh, I guess there's one more here. One more. If I took the derivative that's bottom, I'd get 3, right? So we have to multiply the top by 3. All right, but if we do that, we change it. We change the equation, so we actually have to bring a 1/3 to the outside. So this y is what I have in black here is 1 over 1, right? So I didn't really change the equation, just manipulate it a little bit. So now we can take the integral. So our integral is going to be the natural log. So it's going to be 1/3 times the natural log of 3x plus 2 plus c. All right. Another example, maybe we, okay, so we're doing some problems. We look at the derivative of the bottom, that's going to be 2x. That's nowhere near what we need it to be for this example here, for this integral here. And so maybe we could try something else. We can figure out the factor. You know, we can try to factor this down. You notice that x squared plus x plus 1 doesn't factor down very easily. But what we can do in order to find a factor of a function, we can go ahead and use our long division. And I know it's been a while since we've done this with functions. We should still be able to do it. X squared plus x plus 1. Remember, we look at what we need to take times this in order to get an x squared here, because we're going to subtract just like regular division. And you notice I only have to take it times a 1. Well, my 1 goes over here. It doesn't go with the x on top of the x squares or on top of the x. All right, so I take it times the next squared. So I have x squared plus 1. And if you remember, anytime you divide, you're subtracting. So my x squareds cancel out, and my 1's cancel. I'm left over with an x. And I can't do anything about that. I can't multiply this over here by anything to get just an x. All right, so that actually is my remainder. So what we can say is a factor of this, it would be 1 plus, and you write remainders when you're dividing as our remainder all over what we divided, right? So we divided, so sorry, we have x all over x squared plus 1. So I should have my remainder all over what I divided by, so x squared plus 1. Now we can take the integral of this. Very simple. We take the integral of these separately, so we're going to take the integral of them separately because it's addition, and we know that. The integral of 1 is just x with respect to x, 1 dx, by the way. And then the integral of x all over x squared plus 1. Well, if you look, the bottom, if we take the derivative of the bottom is 2x. Now, so we have to do something up top. We need a 2 up there. If we put a 2 up top, we got to have a 1 half out front. So it's going to be plus 1 half. You notice now we've fallen into our pattern. It's just going to be the natural log of x squared plus 1 then, plus c. All right, so just a quick review. If you get stuck on a problem like that, you can certainly work it out that way right there using long division. All right. All right, example 6. Evaluate 2x all over x plus 1 squared. Now, it appears to me that I have a function inside of a function. All right, so we might be able to use a u substitution. Let's try that. Let's use a u substitution and say u equals x plus 1. All right, so then du equals dx, right? But we really haven't done too much because now we haven't canceled that darn x out. So we just have a u squared up there. All right, and then du equals dx, so this is a du. Normally, remember, when we use a u substitution, we wanted this x to cancel out here. Well, we can fix that. We can solve for x up here. Solve for x in terms of u. So x would equal u minus 1. So we can go ahead and we can plug in. We can get all terms of u. So we'll have the integral of 2 times u minus 1 all over u squared. We know from our integrals that we can pull this 2 out. We can, anytime we're multiplying everything by a constant, we can pull it out. So we're at 2 times the integral of u minus 1 all over u squared. And we've done this integral before. We just break it up into 2 separate fractions. So u all over u squared minus 1 all over u squared. All right. So then we go ahead and we say, okay, well, 2 times the integral of 1 all over u. Sorry about that. 1 all over u, because u divided by u squared is just 1 over u, minus, let's go ahead and let's move this up to be u to the negative 2. So the integral of u to the negative 2. And we know what we're doing. We're just going to increase the power by 1. Or actually, sorry, let's start over here. This 2 is being multiplied by this entire thing. I messed that up. So I have 2 times then, let's see, I just have u on the bottom. That's going to be the natural log of u minus, all right, we increase our power by 1 divided by the new power. So I'm going to have u to the negative 1 divided by the new power of negative 1. So it's going to be plus 1 all over u, right? Because I'd increase my power 1. I'd have u to the negative 1 divided by a negative 1. Well, I had a plus out there, or I had a negative out there, so it changes to a plus. The only thing left to do is go ahead and substitute our u back in. And so the finished product then is 2 natural log of x plus 1 plus 1 all over x plus 1. So we can still use a u substitution, same rules that we have in the last chapter. All right. And just 2 more examples for you. The differential equation. All right. Well, if we're solving the differential equation, we want to get y. All right. So we want to take the integral of both sides is what that's saying. We take the integral of dy over dx. We're just going to get y equals now 1 all over x plus natural log of x. If you try to make a u substitution, if you try to make x, all right, make u equal to x, then du equals 1. Doesn't really do anything for us. If we try to make it x natural log of x and try to take the derivative of that, we're going to have to do the chain rule. That's not going to work. Let's go ahead. Let's make u equal to natural log of x. We can make as many. We can choose whatever we want for u. Let's make it the natural log of x. So u equals the natural log of x. Let's take the derivative of that. So du equals the derivative of stuff over stuff. So 1 all over x dx. All right. So then du or dx equals x times du. So when we plug in for dx, we're going to have x times du in for that. So we'll have 1 all over x natural log, or 1 all over x times u. My bad, I substituted u in for that. U, and then we're substituted in for our dx, so x dx. Notice that these x cancel out. Perfect. So now I'm taking the integral of u. Sorry, this should be a u, du down here. Taking the integral of 1 all over u, which we know is just going to be, so y equals the natural log of u plus c, all right? And then we just go ahead and we plug our u back in. So y actually equals a natural log of the natural log of x plus c, okay? Well, all I did is I plugged u back in. So sometimes you got to play around with what u substitution you're going to use. And the last one here, the integral of tangent x. Just to show you how we can do this, we can break tangent into, if you remember from our trig days, the sine of x all over cosine of x. All right. If you let the bottom, if you think about this, the derivative of the bottom, derivative of cosine is negative sine. So in order to get the top to look like the derivative of the bottom, we have to multiply it by a negative. Well, if I do that up top, I also have to multiply by a negative on the outside. All right, so now I have the derivative of the bottom up on top. So it's just going to be minus the natural log of cosine. So stuff plus c. All right, and for more information on those, there's 6. I just want to show you how they get that, but there's an example. There should say there's more examples on page 326 to see the integrals of 6 basic trig functions. All right. So there's our video for tonight. Hope it helps. We'll see you in class.